All right, the second part here, we're going to look at hydrogen bonding and then an overall kind of practice problem for all these different types of intermolecular forces. So hydrogen bonding is actually a type, or still now being classified as a type of dipole-dipole. Now, there is some work being done right now with hydrogen bonding where they're trying to kind of reclassify it actually as its own bond. It's actually a very, very strong intermolecular force, and so some people actually want to classify it actually as its own bond, like a covalent or an ionic, but I don't think we're quite there yet, at least as it concerns the AP test. Okay. Water has a stronger intermolecular force than most dipole-dipoles, which is what led to this hydrogen bonding thing. How they noticed that was kind of by its boiling point. Okay. And so we looked here at water, and you see the boiling point of water is a lot higher than its counterparts, okay, of elements in the same kind of group. We've got O, S, S-E-T-E, and they're all bonded to H. And what we notice about here is that this boiling point is so much larger than any of the other ones in its group, even though it has the same number of electrons that you are sharing, okay? So what happens here, okay, is that it looked at a couple other examples as well. So people saw that NH3 and HF also had higher than normal boiling points. So people were wondering exactly why this happened. Okay, so we're going to talk a little bit about what exactly a hydrogen bond is. But it came about from looking at water, okay, which is probably the most typical kind of hydrogen bond. Okay. The strong attractions in water are the result of hydrogen bonding. Okay, this is a special type of intermolecular attraction that is between the hydrogen atom in a polar bond, okay, and the non-bonding electron pair. And it needs to be an F, an O, or an N atom in another molecule. Okay, it's got to be H with either a corresponding F, O, or N in a molecule next to it. And these are again considered unique dipole-dipole attractions. Okay, and they come about because F, O, and N are so electronegative that a bond between hydrogen and any of these elements is very, very, very polar, with hydrogen being the positive end. Well, since hydrogen has no core electrons, that means the positive side of the bond has the concentrated charge of the partially exposed. And it's nearly a bare proton for the nucleus of hydrogen. So what you really have here is a positive proton in the form of hydrogen, okay, and then it is bonded to or attracted to a very, very electronegative F, O, or N. So you've got a really, really negative charge and pretty much a total positive because you're not really only have a proton. And so you get a very, very strong attraction. And again, it's between two molecules. So it's between two waters, not in one water. Okay, it's the negative of the O and the positive of the H. Again, it's a positive with the H because hydrogen is very, very low electronegativity. It doesn't want electrons at all. Okay, it would much rather be positive. So it gives its electrons to something very electronegative, O, and these are actually pretty much a whole positive and a whole negative, very similar to an ionic bond. Okay, which makes them stronger than any other type of intermolecular force, which is why some people want to call them their own bond. Okay, hydrogen bonds are weaker than chemical bonds for the most part, okay, but they are stronger than dipole-dipole or dispersion. And the lower density of ice compared to that of water can be understood in terms of hydrogen bond attractions. Okay, in an ice-water molecule, okay, they assume an ordered but open arrangement as seen below. This optimizes the hydrogen bonding interactions between molecules, with each water molecule forming hydrogen bonds to 4 other water molecules. So you end up kind of with a box. Okay, you're going to have an H2O. This O is going to be bonded to an H on a different one. Okay, then we've got another H on a water. And you're going to have another one, and you end up with like this box. Okay. Now, these hydrogen bonds create open cavities in the structure. When ice melts, the cavities collapse and liquid water becomes more dense than its solid form. Okay, most solids are going to be more dense than their liquid because solid particles tend to be very close together. So you're going to have more particles in that same volume. Well, not that way for ice because of the hydrogen bonds that it creates and the open cavities of air that you actually have in water. You got to think about if ice did not float on top of water, then life would be much different. When a lake freezes, just the top water freezes right now, okay? And the sheet of ice insulates the water below. If ice was more dense than water, the ice would sink and the whole lake would freeze. So we really need this idea that water is actually more dense than the ice form of water, okay? Again, notice here how you've got these open cavities in between, okay? So let's look at an example here. Okay. Says practice, in which the following substances is hydrogen bonding likely to play an important role in determining physical properties? We've got methane, okay, CH4. We have hydrazine, which is H2N, NH2. We have methyl fluoride, CH3F. And we have hydrogen sulfide, H2S. Okay. Now when we look at CH4, for hydrogen bonding, we need an H and either an N, an O, or an F on the neighboring molecule. Well, there's no N, O, or F here. So this is not going to have any hydrogen bonding. All right, let's look at the next one. We have an H on the outside that could bond to the N in the middle of another molecule. So we can definitely have hydrogen bonds here because you've got the N and an H. Now, CH3F, okay, when we look at this, you've got CF bond, so I'm going to have C with an F and then HHH, okay, but it's not an HF bond, okay, so no hydrogen bonding. It's not an HF, okay. Now I've got an H2S, so I'm going to have H bonded to an S. But this S is not N, O, or F, so no. The only one you have is this one because the N's and the H's are bonded together. Because this one here won't make it polar enough. Okay, CF is going to be polar and CH is going to be a polar bond, but it's not going to be polar enough to even when another hydrogen comes along here and another CF, CH3F, this bond here is not going to be a hydrogen bond because it's not polar enough. Okay, so let's kind of take everything in here. And you have this kind of flow chart. Okay, interacting molecules or ions. You can have one of three things here. Are there ions involved? If there are ions involved, okay, then you go to the right. Are polar molecules and ions present? If they aren't, you've got ionic bonding. If they are, you've got an ion dipole. Okay, if you don't have ions, then do you have polar molecules? If you don't have polar, then you have dispersion. If you have polar, you're either going to have a dipole-dipole or hydrogen bond. Okay, so let's try this example here. It says list the substances BaCl2, H2, CO, HF, and Ne in order of increasing boiling points. So we need to know what type of intermolecular force these molecules exert. Okay, BaCl2, we've got a metal and a nonmetal, which is going to make it ionic. H2, I'm looking at covalent. Now it's a covalent bond. Is it polar? No, it's an H bonded to an H, so it's nonpolar, which means it has to be a London dispersion force. Okay, I've got CO, two nonmetals, covalent. Is it polar? Yes. How I know it's polar? Because it's not the same thing bonded to itself. So it's polar. If it's polar, now is it hydrogen bonding or is it dipole-dipole? Well, there's no hydrogen there, so this is dipole-dipole. HF, that is covalent. Okay, we've got two nonmetals. Is it polar? Yes, they're not the same. Is it hydrogen bonding or dipole-dipole? This is a hydrogen bond because it has an H bonded to an F. Ne has a covalent bond. It's just a nonmetal. Is it polar or nonpolar? Nonpolar. So we've got London dispersion forces again. So now I'm going to rank them here. Okay, my highest boiling point is going to be BaCl2 because it's an ionic bond. And it's going to be the strongest. Okay, the next strongest is going to be my hydrogen bond, HF. Then I've got my dipole-dipole, which is CO. And now we've got two London dispersions. So how do I know which one is stronger? Well, that's the one that is more polarizable, which is going to be the larger molar mass. And my larger molar mass is Ne. And then H2 is last.